Welcome to video 3.3. This is chapter 3, where we discuss the properties and differences between substances and mixtures and the different types of each. We defined a substance earlier in the year as matter that has a uniform and consistent composition, which means it's the same stuff in the same proportions no matter where you find it. And most substances in the universe exist in one of three main states: solids, liquids, and gases, which we'll discuss in more detail later. And they have different physical and chemical properties for the same substances depending on what state you're in. So examples of substances, and just to show you, iron, the element Fe, is the exact same stuff, the same substance, the same composition, whether you find it in a metal ore or in a tool or other device, in a frying pan, or, alright, well that might be a little different, but table salt. Table salt is sodium chloride, and it's one sodium, one chloride ion, no matter where you find it, whether it's on your table, in a refining plant, in a mine underground. It is always NaCl. Same stuff, same proportion. Water is always H2O, whether it's in the ocean, in your bottle that you drink, or at Niagara Falls. It's always H2O. One oxygen, two hydrogens. Now within substances there are different classes. An element is a pure substance that cannot be broken down into anything simpler by physical or chemical means, which means you can break down substances into finer and finer pieces, different substances, up to a point. There's a certain point where you can no longer break that substance down into anything else with a chemical reaction or a physical filtration process. At that point you have reached elements. Those are the things on the periodic table. If it's on this table, it's an element, which also makes it a substance. And a compound is a substance made up of two or more elements. Okay, so you've got combinations of elements that form compounds. They're bonded together chemically. You cannot separate these things by physical means. You can separate them with a chemical reaction, but not with a physical process. You cannot take H2O, put it through a filter, like a coffee filter, and get hydrogen plus oxygen. It doesn't work that way. A mixture is a combination of two or more substances. Those could be elements or compounds or both, but they're not bonded together chemically, they're just mixed physically. Each substance keeps its individual properties. There are two different types of mixtures. The first is called heterogeneous, which is a mixture that's not evenly blended, and you can still pick out the individual components of the mixture. Some pretty common examples. Here's just a mixture of different kinds of beans and rice and things like that. You can see each piece individually. You can see that they're not evenly blended, so you could take a spoonful from the top and get different stuff from a spoonful at the bottom. A salad, same thing. You can see the tomatoes and the cheese and the onions, and you could pick them out. The olives are separate. You take one forkful, you get one mouthful of food. You take another forkful from a different part of the bowl. It's a different combination. That's heterogeneous. The ocean, even though water is a substance, the combination of all the things in the ocean represent a heterogeneous mixture. There's different stuff off the coast of Massachusetts compared to the coast of California or the coast of South America or elsewhere in the world. Different mixtures. A homogeneous mixture is a mixture with a constant composition. Now this doesn't make it a substance. It's just that the mixture is so evenly blended that you can no longer see the individual components. So metal alloys like steel or the air around us are examples of homogeneous mixtures. You can't pick out the oxygen and nitrogen that are in the atmosphere around you. Things like apple juice or coffee or tea are homogeneous mixtures, assuming you haven't put milk or sugar and things in them, because you can't look at this cup of apple juice. It's not a very great image, but you can see right through it. You can't see the different parts of the solution. Stainless steel is a mixture of different elements that combine to form a new compound, a new mixture. Now you could separate out the iron from the carbon from the nickel, that are in stainless steel by different processes, physical processes, but you can't slice one of these ball bearings in half and pick out the different layers. And homogeneous layers are very often what we call a solution. So a solution of liquids usually, or a solution of gases, but alloys like stainless steel are solid solutions. Mixtures, unlike compounds or elements, can be separated into individual components by a physical process, and there are a variety of different processes that we're going to look at. The most common and simplest way to separate components of a mixture is through filtration, where you have a filter of some kind. This filter paper in this example, you put it into something like a funnel, you pour a liquid into the funnel which has some sort of solid mixed into it. The solid gets trapped in the filter, the liquid is allowed to pass through, and this is called the filtrate down here. For example, sandy water. You pour sandy water in there, the sand gets caught in the filter, the water is allowed to pass through, and then you've gotten the separation of the mixture. Chromatography is somewhat similar to filtration. It takes advantage of the fact that different substances will travel through what's called a medium, which in this case is this special type of paper, at different speeds. So you can see here, this is black ink up here. Down here, the black ink has broken down into its individual components. So the blue and green, which are up here, traveled the least distance. The red and the yellows farther down travel a little bit faster through the paper. So you've actually separated the dye into individual components. The same here, the green is broken up into the blue and yellow mixtures, but they pass through this filter paper at different rates. So if you allow the process to go to its finish, you get different things spread out and separated from one another. Distillation is something that takes advantage of the fact that different substances have different physical properties. So boiling point in this case, you have a mixture of liquids here, you heat them up with a Bunsen burner, and the part of the mixture that has the lowest boiling point is going to boil first. It's going to turn into a vapor and escape from the liquid. It's going to go up this column, it's going to start to cool down again and form a liquid, and that liquid can be sort of trapped off to the side, and you've separated one of the liquids from the other liquid. This liquid doesn't get hot enough to boil, so it stays in that round bottom flask. Crystallization is when you have something dissolved in a liquid. You allow that liquid to evaporate. The first and least soluble substance crystallizes first, in this case sugar crystallizing out of water, and you get something like rock candy or other things too. Sublimation is not very common, but it takes advantage of the fact that some solid substances go directly to a gas with no liquid in between. It's somewhat like distillation in that you can get this gas out of the solid, trap that gas, pass it off somewhere else, and you've separated it from the other stuff that might melt first before it boils or sublimes. And the formula that we're going to be using here is called percent by mass. This is a new formula. It's similar to the percent error formula that we used before, and it's similar to a lot of other formulas that we're going to use. We use percentages a lot. So what we're doing with percent by mass is we're expressing relative proportions of substances in a compound, and we're doing it based on the mass, not necessarily how many atoms of each element are in a compound, but how much mass each one makes up in a percentage of the whole. The formula is here. Okay, the percent by mass is equal to the mass of the element you're looking for divided by the total mass of the compound. Make sure it's the total, and then you multiply it by 100 to get your percentage. So let's do an example. If you have a 78 gram sample of unknown compound, you can identify that it contains 12.4 grams of hydrogen. What is the percent by mass of hydrogen in the compound? Okay, so percent by mass equals the mass of the element. In this case, we're looking for the hydrogen, and we said that was 12.4 grams, divided by the mass of the compound, which is 78 grams times 100. You do that out, and it comes out to 15.9%. Make sure you check your significant figures on that answer. Okay, so 15.9% hydrogen. It doesn't mean there's 15 hydrogens for every other atom. It just means that if you did all the mass, 15% of that mass comes from hydrogen. All right, so I'm going to do a couple more examples. What I want you to do is look at the example, pause the video, try to answer the problem, and then play the video again, and I'll work the problem through. A 1 gram sample of hydrogen reacts completely with 19 grams of fluorine. What is the percent by mass of hydrogen in the compound formed? So pause here, try to work out this question, come up with your answer, and then come back, play the video, and you can check your answer against my work. Okay, so a 1 gram sample of hydrogen reacts completely with 19 grams of fluoride. What's the percent by mass of hydrogen? So again, percent by mass is going to be the total on the bottom, which is 20 grams, with the mass of the element on the top, which is 1 gram of hydrogen, times 100, and that comes out to 5%. Now, if you, instead of 5%, got 5.26%, or something very close to that, that's because your denominator was only 19 grams. Okay, and 19 grams is how much fluorine was in the compound up here, but it says that the 1 gram of hydrogen combines or reacts with the 19 grams of fluorine. So the whole thing together, according to the law of conservation of mass, weighs 20 grams. So make sure you keep track of that when you're doing these problems. Next problem. If 3.5 grams of element X reacts with 10.5 grams of element Y to form a compound XY, what is the percent by mass of X and the percent by mass of Y? So we're going to do each element separately this time. So pause here, work out the problem, and then come back and we'll go through it together. Okay, so first we're going to do the percent of X by mass, and the mass of the element X is 3.5 grams. The mass of the compound, make sure you check this, okay, 14.0 grams. You have to combine element X and element Y. So if you had 10.5 on the bottom, you weren't taking into account the whole compound. Multiply that by 100, and you get 25% X by mass. Okay, and then if we do the same for Y, percent Y is 10.5 divided by 14. And if you did divide it by 10.5, this should have been a clue, because you would have come up with 100% for Y, which wouldn't leave anything for X. Okay, times 100 is 75%. 75% Y, and this was X. Now, notice that if there are only two elements, X and Y, then in order to find, once you find the first one, 25% X, well, you could find Y by doing 100 minus 25%, and you'd find 75%. Since they both have to add up to 100%, that will always work if you only have two elements. So in this problem we have two compounds, compound 1 and compound 2. 135 gram sample of compound 1 has 15 grams of hydrogen. A 34 gram sample of compound 2 has 2 grams of hydrogen. Are these the same compound, or is it possible that these are the same compound? So pause this here, try to work this out, and we'll be back in a minute and I'll work through it with you. Alright, so we've got two compounds. So we're going to do percent by mass of hydrogen in compound 1, percent by mass of compound 2, and this is both for hydrogen. So for the first compound, we've got 15.0 grams, and it says the total mass of the sample, so we don't need to add anything together here. It's 135. I'm going to multiply that by 100, and that comes out to 11.1%. Make sure you check your significant figures on that. So that's hydrogen in compound 1. In compound 2, it says we have 2 grams out of 34 grams. Again, that's the total, so we don't need to add those two together. And if you work out the percentage on that times 100, it comes out to 5.9% for compound 2. So the question is, could these be the same compound? The answer here is no. If you do not have the same percent composition of any element in the compound, they are not the same compound, because a compound, which is a substance, must have the same proportions every time. So if the proportion or percentage is different in two samples, they cannot be the same compound.